Alright gang, let's get into lesson 2, which is all about Newton's laws and how to apply these things. This is really getting into the heart of the matter here because with Newton's laws, that's what we're going to be using to develop these equations of motion that we'll be using for the rest of the quarter. So let's just briefly discuss these. Law number 1, which says every body perseveres in a state of rest or of uniform motion in a right line, unless it is compelled to change that state by forces impressed thereon. So the whole point of this first law was really Newton taking a jab at Aristotle. We've mentioned this in class before, but it is rejecting the Aristotelian notion that for movement to occur, you have to have a force. Okay, because the first law is saying that if something is already in motion, then to change the motion, it needs a force. And we've said that the Aristotelian motion was essentially saying that we had F equals mv. Force equals motion, it requires motion. And really that's kind of a conclusion that's easy to come to because we say you got a force and you see motion, and this is where we get the idea of state that we discussed in the last lesson, in which what we can observe is position and what we can observe is movement or velocity or speed. We can't really observe acceleration. So it was kind of a natural conclusion in ancient philosophy to say F equals mv, or to have that type of idea. So then what follows that is the second law, and in the book it was stated as the alteration of movement is ever proportional to the motive force impressed and is made in the direction of the right line in which the force is impressed. And in fact, that's very similar to what Newton wrote in Principia in the 1700s. It says, a change in motion is proportional to the motive force impressed and takes place along that straight line. And so Newton's second law then really gives us this new formulation of saying it's not F equals mv, but now F equals ma. But in particular, F equals ma didn't show up in Principia. But instead, it was this kind of strange formulation of motive forces and all that kind of business. So the form that we're going to introduce here, we all know F equals ma. But in reality, it's F is equal to d dt of mv. Alright, so a couple things to notice here is that it's mv, and mv is linear momentum. So another way to write this is the time differentiation of p, which is linear momentum. Now we need to observe all of this, remember, is that we're taking our time derivative, and that needs to be in the inertial reference frame, and our velocity needs to be in the inertial reference frame, and our momentum needs to be in the inertial reference frame. We're going to get to this a little bit later. Interestingly enough, the first law helps us make more sense of an inertial reference frame from the perspective of what we call Newtonian relativity. Alright, so then law number 3, you've seen this before. To every action there's always opposed and equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. And you've all taken a statics course, so you have seen this before. You've dealt intimately with this about how forces are transmitted through objects. So let's just jump right into the meat. And I want to work through these 3 examples that we saw in this section of the book. Example 2.1, 2.2, 2.3. And just be sure that we really understand this. And what we're going to do is we're going to drop the vector notation for a moment, because we're only going to talk about straight line motion. And in straight line motion, we can do this all with scalars. We'll just skip the vectors. But let's draw a diagram to be sure that we're all on the same page. So in straight line motion, I'm going to draw a wall, and that's going to be our origin. We'll call it 0, O. We're measuring x from that point. So positive x is going to be to the right, negative x would be to the left, and we have a particle that's moving on a line particle has a mass of m, and then it's being acted upon by a force. We'll draw it as a vector, and it's a force in the x direction. Okay, so notice I didn't put any vector notation here at all. It's all scalar notation. And so when we are defining the position of this particle, we get rid of this. We're defining our position, and we're saying that the particle is a distance x away from the origin. So x is our coordinate. Now, if that's our position, x, then we can define the speed. So the speed is x dot, which is dx dt. And then we can also define the acceleration, x double dot, which is dx dot dt, the time differentiation of the speed. Okay. So now also recall that we have a here on the x, that's an implied t, and also on the x dot, that's an implied t. All of these parameters, the position, the speed, the acceleration, are all going to be functions of time, because that's really what we care about. We care about how these dynamic systems evolve over time. So in this first instance, example 2.1, we're looking at a straight line motion with no force applied. And so straight line motion with no force applied is going to be fx is equal to 0. Right? On the drawing, that force vector doesn't exist. And so if we apply Newton's second law, we're saying Newton's second law is f sub x is equal to m x double dot, and then we're going to say f of x is actually equal to 0. And so this now implies, what follows from that is that x double dot is equal to 0. So acceleration is going to be 0. Now this is our equation of motion. X double dot is equal to 0 is our equation of motion. It's a second order differential equation. So recall that we want to find the state of the system using our second order differential equations. The state of the system is the position and the speed. So we're going to take this and we're going to solve for the position and the speed. We just said that x double dot is equal to dx dot dt. All right, so let's substitute that in. So we have x double dot is equal to dx dot dt. We know that that's equal to 0 in this problem. And so if we integrate, then we get the integral of dx dot, and then we've multiplied through by dt using our Leibniz notation, and so that's equal to 0. And when we integrate this, we get that x dot, and I'll put in the time t, showing it's a function of time, and we have to have an integrating constant. So there's our constant c1, and that's equal to 0. So now what we're saying is that with this x dot, okay, if we know what our constant is, then we are now going to know x dot as a function of t for all times. And so we solve for this. We say that x dot as a function of t is going to be equal to negative c1. All right? So this tells us that the speed is constant. So x dot t is going to be a constant. If we know the initial speed, then we know the speed for all times. The initial speed meaning when time is equal to 0. And so when we apply that boundary condition, we say that x dot t is going to be equal to x dot at time 0. And so now we know the speed of the particle. So now it's time to solve for the position. All right, let me move these out of the way so we've got room to work. And, all right, so let's solve for our speed. All right, we said before that x dot is equal to dx dt. and that x dot, we now solve for this, is equal to our initial condition. All right? And so we want to rearrange this. And so if we rearrange it, we're going to get dx is equal to x dot of our initial condition. And we get our dt. We want to integrate both sides of this. And when we integrate both sides, we'll get x of t plus an integration constant, c2, we'll call this. And then this is going to be equal to, when we integrate the right-hand side, x dot at time 0 multiplied times t. Once again, if we know the position at time 0, if we know the position at time 0, that's our boundary condition. And so with this position, we can substitute this in and say that at time is equal to 0, we have our initial position plus c2 is equal to our initial velocity, and then it's at time 0, so we put in 0 for the time, which makes this entire right-hand side equal to 0, and then therefore c2 is equal to negative x at the initial position. So then this gives us the expression for position at any time of xt is equal to the initial position plus the initial velocity multiplied times t. And so now we've fully solved for the state of this particle system when there is no force applied, starting with our equation of motion, which was x double dot is equal to 0. All right, now we'll move to an example that I'm certain that you've seen from physics, and that is straight line motion with a constant force. So for a constant force, we're saying that we have a constant force f of x. And in that case, we have f equals mx double dot. And so to get our equation of motion, our equation we solve for x double dot, and our equation of motion is x double dot, is equal to f of x divided by m. We're going to integrate both sides, just like what we did before. We're solving our equation of motion. When we integrate both sides, we get that x dot t plus an integration constant is equal to f of x divided by m multiplied times t. So we're integrating both sides with respect to time. Okay? And so we just add the t to the side because we said that f is constant, and we know that the mass is constant as well. It's not changing over time. So that's why when we integrate with respect to time, then we can simply multiply by t. So this is telling us that speed is not constant. So we still have to apply our boundary conditions to get this into working form because we still have a c1 that's hanging out there. So at time is equal to 0, our initial condition, x dot t is equal to x dot 0. And so we apply this, substitute this in the equation. So x dot at the initial time plus c1 is equal to f of x over m. And then this is at time is equal to 0. So we're putting in a 0, which makes the right-hand side become 0. We solve for c1. And so c1 is equal to negative x dot at the initial time, 0. And so our equation for the speed is x dot at any time t is equal to our initial speed plus fx divided by m multiplied times t. All right, so that's our equation for our speed given a constant force. And so what we see here is that the speed is going to be increasing, at a constant rate, or decreasing at a constant rate, depending on whether that force is positive or is negative. So let's solve for position, and to solve for position, we're going to substitute this in where we've got dx dt is equal to x dot, and this is equal to x dot at time 0 plus f of x divided by m multiplied times t. And then we're going to integrate both sides. We're going to multiply through by t and then integrate both sides, which will give us dx and then x dot at our initial time dt plus f of x divided by mt dt. And here's where we integrate both of our sides. Okay. And then when we do this, we get our position as a function of time plus the next integration constant we call C2. And then equal to, on the right hand side, the initial speed multiplied times t when we integrate that expression, plus f of x divided by m t squared divided by 2. We apply our boundary conditions, and when we apply the boundary conditions, at time is equal to 0, we know that our xt is equal to our position at 0. Substitute this in, so we get initial position at 0 plus C2 is equal to our initial velocity. Okay, it's multiplied times t, so it's multiplied times 0, which gives us 0 for that expression. Then plus f of x divided by m, and then it's t squared, so it's at time 0, so 0 squared divided by 2. That expression is also 0, and then gives us a final expression for our position that's position at any time t is equal to the initial position plus the initial speed multiplied times t plus f of x divided by m t squared over 2. Alright, so we now have scalar equations for a particle that's undergoing a constant force, or has a constant force, but this is also equivalent to a constant acceleration. A constant acceleration that is the force in the x direction divided by m. You guys have seen this from physics. This was kind of one of the fundamental equations that you probably wrote down on an equation sheet. But what you were actually doing is that you had an equation of motion. You had an equation of motion that was, we called it x double dot is equal to an expression, and then you solved the differential equation analytically so that you obtained the state. This is the new terminology that we have in dynamics. Alright, so let's address an even more complex situation that you may or may not have seen before. But this is where we have straight line motion, and then we have position that is now feeding into force, or force is a function of position. So in this scenario, we start out always by writing an equation of motion, which is x double dot is equal to, and it's our force in the x direction, but it's a function of x. Last time it was constant. The first time we had no force. This time it's a function of position. It's a function of x. So in the past two examples, we've integrated both sides by time. And so if we take this expression, all right, and then if we wanted to integrate both sides by time, dt, and then dt, then we've got an issue here. We can't simply just say, all right, we're going to integrate both sides by time, we'll just throw some t's on there and get along with our lives. And the reason why is because is because the force is a function of x. The force is a function of x, and then x is a function of time. Remember, our position is always a function of time. That's implicit in there. And because of the stacking of these dependencies, we simply can't just integrate by time because time is buried within this x expression. So we've got to be a little bit more creative with this, and we need to separate our variables. And so to do that, here's going to be the procedure. Instead of multiplying both sides by dt and integrating, we're going to multiply both sides by dx. Now, you should still bristle with this just a little bit because, as you notice, we have the right integration variable here because we have something that's a function of x. M is our mass, it's constant. But on the left-hand side, we're still mismatched. We have x double dot, and then we're trying to integrate with respect to x. So we still need to get this into a form that we like, and we're going to use some substitutions. Now recall that we defined at the very beginning that x double dot is equal to dx dot dt. So the acceleration is equal to the time differentiation of the speed. And so what we're going to do is we're going to substitute that into the left-hand side so that we have dx dt multiplied times dx. So it's dx dot dt multiplied times dx on the left-hand side. And our right-hand side, remember, we're satisfied with that, so it stays the same. F sub x is a function of x divided by the constant m dx. Now, because this is Leibniz notation, okay, we can take this expression here, and we've got dx dt. And dx dt we defined earlier as speed. So x dot is equal to dx dt. So we can just substitute that right back in. And so now that we have the expression x dot dx dot is equal to all the expression on the right hand side, f sub x as a function of x divided by m dx. So now we have everything in terms that we like. So it's x dot, and the integrating variable is x dot. On the right hand side, it's fx as a function of x divided by m, and the integrating variable is x. So now we're ready just to integrate. So we're going to integrate both sides. Now we're integrating both sides by two different variables, which means that we need to apply two different boundary conditions to these variables. And so our boundary conditions now are, we need to have time 1 and time 2. And so the boundary conditions on the left-hand side are going to be the speed at time 1 and the speed at time 2. And on the right-hand side, because we're integrating across position now, it's going to be the position at time 1 to the position at time 2. And so we've got the right form to integrate, we've got the right boundary conditions, and so now we simply integrate. And so to integrate the left-hand side, it's x dot squared divided by 2, using the fundamental theorem of calculus. We're going to apply these boundary conditions. X dot at time 1 to x dot at time 2. And to integrate the right-hand side, we actually just have to leave that one alone because this function is a general function and it's currently undefined. And so we'll leave that as the integral of f of x as a function of x divided by m integrated across dx, and the boundary conditions of x at time 1 to x at time 2. Right? So in the book, if you're following along in the book, then you can see that they substituted And they said that x dot t is equal to, this is a new t, so the speed, and then also that f of x is a function of x divided by m, they defined as a as a function of x, so an acceleration as a function of x. And so that makes the notation a bit more general, okay, in which we say that we have, now it's the speed squared at time t2 by making the substitution is equal to the speed squared at time t1, and then plus, we move our denominator over, 2 multiplied times the integral evaluated from x at time 1 to x at time 2 of the acceleration as a function of x dx. And so, given an expression, this is now relating the speed, or what we call the scalar velocity, directly to the position when we know the function, when we know acceleration as a function of x. Okay, so we have to know acceleration as a function of x to be able to then figure out that state. And remember, in this case, the speed is intimately related to the position. All right, so this is the heart of equations of motion. These are the first examples that we've had where we've worked, start to finish on this. They're all second-order differential equations that we solve to obtain the state, position, and speed. Never forget that. Sometimes we have to be clever to solve them. We have to use our bag of tricks from differential equations, or we even solve these numerically, and that's what we'll be working on in the laboratory. All right, let's talk briefly about one more caveat in Newton's laws that's really important to keep in mind, and then relate this back to our discussion about reference frames. So a really important part about Newton's second law is that it does not apply everywhere. And that may sound like kind of a funny statement, but it's absolutely true. It depends on your reference frame. And so Newton introduced this idea in Principia, that these laws are only observed, or only valid, when observed from absolute space. And as you saw in the reading, absolute space is just one of several vagaries that Isaac Newton introduced in Principia, along with force and mass and some other ideas that he actually took some heat over. And so he said that this absolute space is relative to the quote-unquote fixed stars, which actually still leaves us scratching our heads because, well, stars just aren't fixed. Well, since Principia, we have adopted a much more precise vernacular and language about reference frames in which Newton's laws apply. And so what we do is we call this an inertial reference frame. Newton's second law can only be applied if observed from this wonderful, special, magical reference frame. It's an inertial reference frame. Now, we're going to develop these ideas a little bit more clearly, but we're going to do that later, but an important thing to remember is actually this idea of what we call Newtonian relativity. And this is that there's no such thing as just a single reference frame. There are multiple reference frames, inertial reference frames. And so an inertial reference frame is any reference frame moving at a constant velocity and not rotating relative to another inertial reference frame. Okay, that is also an inertial reference frame. And so just think about that for a moment. But this is actually getting back to what Newton in his first law stated, is that something that's moving is going to continue moving in that same direction unless acted upon by another force. And so some scientists would say that Newton's first law actually helps us define an inertial reference frame because of this idea of a constant velocity, no accelerations being applied. And we'll talk more about that in class. I want to leave you with one excellent figure from the book, and this is of the vector form of Newton's second law. whenever you're stumbling around with this reference frame notation, when you're looking at what's a vector, what's not a vector, where do I need to put my reference frames, I think that this formulation is just invaluable. This essentially says what we said at the beginning, which is that the force applied at point P, this point mass, is equal to the time derivative as observed in the inertial reference frame, or reference frame I, of the linear momentum of the particle P with respect to the origin of the reference frame observed in the inertial reference frame. That's F equals ma. And then here you see it in the ma component. Notice that just like velocity, we always need to define where we're observing the acceleration of point P with respect to O. All right, I'll see you in class tomorrow, and come with your questions.